All right, so our final colligative property is osmosis, right? So before we start talking about solutions and osmosis, let's first take a look at what osmosis is. So osmosis is defined as a solvent diffusing through a semi-permeable membrane. And so what a semi-permeable membrane means is that the solvent can go through this membrane, but the solute cannot, right? So let some stuff through, but not other stuff. And so there's a huge amount of biological applications when it comes to this stuff. Right, most of your cells are semi-permeable, and there's dialysis, that kind of stuff all goes through osmosis. And so for what we say for osmosis is that the kind of solvent wants to dilute the more concentrated side. And really all of these effects come down to entropy. So we'll learn about entropy later on, and you guys will know the true secrets to how the universe works. But for now, you're just going to have to take my word for it. So the solvent wants to dilute the more concentrated side. However, it's resisted by a difference in pressure. So let's go ahead and take a look at that. So usually we draw it with this kind of tube, and then in here is the semi-permeable membrane. So the solvent can go through, but the solute cannot, right? So we've got some kind of liquid in here, probably water in most of our applications. And then on one side we have a solute. So I'll draw my solute as little purple dots. And so basically what the universe wants to do is have these sides be of equal concentration. So the water on the pure side is going to move onto the side that has the solute in it. And so you can imagine that would then cause a difference in height of the two sides, right? This one lost water, this one gained water, so it's higher up. This is obviously an exaggerated picture, right? And so what we have here is pressure pushing up, right? We're climbing up this wall, we're pushing up. This is what's known as the osmotic pressure. And then of course you have the atmospheric pressure pushing down and opposing those two, right? With, my bad, I forgot to label it, but this is our semi-permeable membrane. So here's just kind of the textbook picture of this. It's the same thing I wrote, right? You got solute on one side, the water goes on that side, and then the pressure is related to this osmotic pressure. And so there's an equation for this, obviously. And so it's capital pi, which is the osmotic pressure, is equal to the molarity times the R, the gas constant, times temperature in Kelvin. So again, this is osmotic pressure. This is the molarity. Remember, that's moles of whatever you're talking about over liters of solution. This is R, our gas constant. And we want to use the 0.08206 liters, atmospheres, moles, Kelvin. And you see that this gas constant is in Kelvin, so this has to be temperature, and it must be in Kelvin. So if you take a look at the units, moles will cancel out with moles. Liters will cancel out with liters, and then Kelvin will cancel out with Kelvin, leaving atmospheres a unit of pressure, so it makes sense for osmotic pressure. And so these problems are relatively straightforward, plug and chug type of thing. So 0.03 molar solution at 37 degrees Celsius. What's the osmotic pressure, right? So remember our pi equals mRT, And so we can just kind of plug and chug. You do have to be a little bit careful, right? This is in degrees Celsius. Our equation must be in Kelvin. So we have to go from degrees Celsius to Kelvin. To do that, we add 273.15. And so this ends up being approximately 310 Kelvin. So we can take this 310 Kelvin and plug it into our T. We're given 0.3 molar, so we can just plug that straight into there. And then we know our gas constant has a value of 0.08206, right? And I showed you how the units worked up above, so the units are fine. And so then you just plug and chug and find that the osmotic pressure is 7.6 atmospheres. So we use osmosis for all kinds of applications. Another useful kind of osmotic property is actually kind of reverse osmosis. Right, reverse osmosis. And so in reverse osmosis, we use this to purify water. And so what we do is kind of push the opposite. So we use a lot of pressure to push water to the pure side. So for example, we have our little tube here with our semi-permeable membrane. Oh man, that's terrible. All right, long day already. Semi-permeable membrane, right? And then on one side, we have a whole bunch of solute. And basically what we're gonna do is we're gonna push down with a lot of pressure. So maybe the stuff on the right side is salt water and you wanna purify it, right? So you're gonna push down on the right side. And so basically you'll force the water to go on the pure side. And then what you'll be left with is a more concentrated salty one on the right side. And then you can keep the stuff on the left to drink or whatever, right? So you have pure water there. We said that this osmotic pressure has a lot of biological applications, and especially for those of you trying to become nurses, right? So this will explain why IVs are saline solutions, right? Salt solutions. And not pure water, right? If you inject pure water into someone's veins, they're gonna die. So that's not good, don't do that. So we can have different situations. We can say a solution is hypertonic to something else, isotonic, and then hypotonic. Generally, we're talking about the solution in relation to the cell, right? Hyper means a lot, iso means the same, and hypo means less, right? If you're hyper energetic, right, that means you have too much energy. Hypothermia, right, that means that you're cold and have a low amount of heat, right? So this is too much salt. Isotonic is the same amount of salt, and then hypotonic is less salt. So generally we're talking about, this probably should have included a solution here, hypotonic solution, isotonic solution, hypotonic solution, right? So if you have a cell and you have a hypertonic solution, the water is gonna wanna leave to dissolve the solution or to dilute the solution. And so what you end up with there is your cell shrivels. And so this is known as crenation. I'm not 100% sure if I'm pronouncing that correctly, but whatever, I'm not a biologist. If you have an isotonic solution, the water is the same on both sides, so nothing's gonna happen there. So you've got a nice healthy cell and you're doing your job correctly. And then finally, if you have a hypotonic solution, right, there's not enough salt in there. So the salty or the less, there's not as much salt inside the cell. There's more salt inside the cell than outside, so the solution's going to go inside, and it's eventually going to expand too much, and then it will burst, right? So that's my little pieces of dead cell there. And so kind of same picture here. right, shows the three different options between too much water going in and the cell bursting, right amount of water, or not enough water. The last thing I'll say is that these problems, although the ones that I did in this chapter seem pretty simple, they can actually be quite a bit tricky. So the only way to really kind of work through this is to practice some. So see your homework and in-book examples for some of this stuff. So there's some good in-book examples on page 634 of your OpenStax textbook.